Hi guys, welcome back. It has been a long time. It has been a long time because I went to India. Right now I'm in India in my college. A lot of things happened, classes happened. I missed 1 week of classes, so I was not able to, give time, do programming, which kind of sucked because I do like programming stuff, learning new stuff. And so finally I've started. Sadly, the videos won't be as frequent as it were during my summer break. They'll be weekly during the holidays. I get 2 days, 2 days holidays, Saturday, Sunday. So I'll try to upload. But yeah, the videos are gonna be infrequent, but this is a start, right? So this is just a start for the videos. I will remove my camera because my room is a bit active. You might see people coming in and out, so I don't want that to disturb you guys. And that will be it. And we're gonna start. So I really don't understand recursion as much as I would like to admit. And so I thought, why don't I read a book about it from AI Swagarat, if I don't know, I butchered the pronunciation. And I have followed his work before, and I know this guy is great. So yeah, let's go. Let's start reading it, and let's see what we can do. Recursion has an intimidating reputation. It is considered hard to understand, but at its core, it depends on only two things: function calls and stack data structures. Most new programmers trace what a program does by following the execution. It's an easy way to read code. You just put your finger on the line of code at the top of the program and move down. Sometimes your finger will loop back, other times it will jump into a function and return. This makes it easy to visualize what a program does and in what order. But to understand recursion, you need to become familiar with the less obvious architecture called the call stack that controls the program's flow of execution. Most programming beginners don't know about this stack because programming tutorials don't even mention them when discussing function calls. Furthermore, the call stack that automatically manages functions call doesn't appear anywhere in the source code. It's hard to understand something when you can't see it and don't know it exists. In this chapter, we will pull back the curtain to dispel the overblown notion that recursion is hard, and you'll be able to appreciate the elegance underneath. I have some idea of the call stack. I mean, I did learn Koa, and the idea this was a bit of socket programming that we are doing in C. I think we should make a video on this. The whole rough idea is, let's say you have a bunch of instructions, and this instruction is like a call instruction, and this is some address over here that you have to execute. We pop that into a stack, so we pop this address one into the stack, and we run this on. This is actually the starting address of the subroutine. We run this, run this, run this, and when it comes to the return statement, we pop this on the stack and put that into the PC. The the definition of recursion. Before we begin, let's get the cliche recursion joke out of the way. To understand recursion, during immersion, I can assure you this joke gets funnier the more you hear it. Another joke is if you search shows a recursion joke from the webcom. I am so meta, even this acronym. I am so meta, even this acronym. I am so meta. Most jokes about the 2010 science fiction or a movie Inception are recursive jokes. The film features characters having dreams within dreams within dreams. And finally, the computer scientists and what computer scientists could forget the monster from complete voyage. The recursive centaur, as you can see, is an half horse, half recursive. Oh my god, what the hell is this? Based on the jokes, you might conclude that recursion is sort of a meta, self-referencing, dream within a dream, infinite mirror to mirror sort of thing. Let's establish a concrete definition of recursion. The thing is something a recursive thing is something whose definition includes itself. That is, it has a self-referential definition. The separation I can't even pronounce it. My mouth is so dry. Is defined as an equilateral triangle with an upside down triangle in the middle. Uh, in a programming context, a recursive function is a function that calls itself. Before we explore recursive functions, let's take a step back and understand how regular functions work. Programmers tend to take function calls for granted, but even experienced programmers will find it worthwhile to review functions in the next section. Cool, cool. What are functions? Functions can be described as mini programs inside your program. They are. I won't be reading it because it's taking too much power out of my mouth. I'll just be going through it, right? And I hope you guys can follow it through my cursor. So functions are code that run, that is values of pass. This is the output function. Though some programming and another function do not run all the time like that. And the program remembers which line of code call the function and returns on it. Different programming languages might have additional features or different options for how to call functions, but they all have these four general elements. Um, yep. You can visualize the first three elements, first three of the name, so you can write them. To get a better sense of program, create function call.py program that has three functions. Okay, let's do that. So I was learning about async IO, so crazy, right? Async IO is amazing. Like I think everyone should learn about it. It just makes you think of coroutines. Things up makes you think about concurrency in a different manner. So recurd. Oh wow. Okay, as Python को तो Python होगा क्या? Oh, it is. Okay, so then recursion. Okay, function call. So I think we'll just make function calls dot py, and essentially this is it. He told me not to copy paste, but I'm a bad boy, so let's see what's happening. So we have A, which A was called, then it calls B, B is called, then C is called, and then print C and then A. Okay, cool. So if you run this in some way of so cd recursion Python function A was called, B was called, C was called, C is returning, B is returning A. This is actually a very good example. The code is equivalent to the following HTTPL. Okay, crazy. When you run this code, the output shows the start of the function ABC. Then when the function returns, the output appears in reverse order. Uh, in other words, functions call doesn't send the execution on a one-way trip. How does the program remember if it was A or B that called the children by? So I think I know it's same like function call stack essentially, and it's a very elegant solution. What are stacks? Earlier I mentioned the cliche why is correct to understand recursion, but this is actually wrong. To understand recursion, you must understand stacks. A stack is one of the simplest data structures in computer science. It stores multiple values like a list does, but unlike list, it limits you to adding to or removing values from the top of the stack only. For stacks implemented with list or arrays, the top is the last item, the right end of the list or the array. Adding value is called pushing values onto the stack, while removing value is called popping values off the stack. Imagine that you are engaged in a mean daring. What does this mean? What does this mean, chat? Uh, follows a
Meandering.
okay. Talking about your friend Alice, which then reminds you of a story about your coworker Bob. But for that story to make sense, you first have to explain something about your cousin Carol. You finish your story about Carol and go over talking about Bob, and when you finish the story about Bob, you go back to Alice. Then you're reminded by about your brother David. Then you're reminded about your brother David. So you tell the story about him. Eventually, get around finishing. Your conversation follows the stack like structure. Okay, so first talk about Alice. Alice goes Bob, Carol. In our conversation stack, the new topics are added on top of the stack and taken off as they complete. The previous topics are remembered underneath the current topic in the stack. We use Python list as a stack. Uh, if to amend the list contents, we limit ourselves to append and pop methods to perform pushing and popping. Note: Python use terms lists an item while JavaScript's. For example, consider the card stack program which pushes and pops string values of playing cards from the end of the list called card stack. So we have card stack dot append 5 more diamonds. We print that. Then we append 3 of clubs, we printed append ace of hearts. The following, we run the program 5 of hearts, 3 of clubs. So उसके ऊपर मतलब it's like pretty much being like, well, this is what we're talking about. Then इसके ऊपर एक और आया, then इसके ऊपर एक और आया. Crazy. The stack starts off as empty. Three strings representing cards are pushed onto the stack. The stack is popped, which removes the ace of the hearts and then leaves 3 of the clubs at the top of the stack again. The state of the card stack is tracked at 3. Yeah, so this is essentially, yeah, you can see the topmost card in the card stack or in our program stack. The topmost value in the simplest stack implementation. You can't see how many cards or values are in the stack. Yeah, that's true. And you can see how he said simplest, not like in ideal solutions you can. You can only see whether the stack is empty or not. Obviously, stacks are LIFO, their structures, which stands for last in, first out. Since the last value pushed onto the stack is the first value popped out of it, the behavior is similar to your web browser's back button. Your browser's tab history functions like a stack that contains all the pages you have visited in the order that you have visited them. The browser is always displaying the web page at the top of the history stack. Clicking a link pushes a new web page onto the history stack. When clicking the back button, pops the top web page off and reveal. Yeah, that's pretty much it. Beauty. Guys, I'm this fever. This like sneezy. I hate. I don't like. Okay, back at it. Programs use stacks too. The program's call stack is also simply called the stack. Is a stack of frame objects. Frame objects, also simply called frames, contain information about a single function call, including which line of code called the function, so the execution can move back there when the function returns. Frame objects are created and pushed onto the stack when a function is called. When the function returns, the frame object is popped off the stack. If we call a function that calls a function that calls a function, the call stack may will have 3 frame objects onto the stack. With when all of these functions return, the call stack will have 0 frame objects onto the stack. So our program also has a stack which is called the call stack, which has frame objects, and frame objects are called frames, and these frames store information about the function that is being called, and also the which line of code that it is being called to. Essentially, pretty much this thing is being happening. Programmers don't have to write code dealing with frame objects in the programming language handles them automatically. Well said. Different programming languages have different ways of implementing, but in general they contain the return address or the spot in the program where the execution should move when the function returns. Yippee. The arguments passed into the function call, the set of local variables created in the function call. Yes. For example, take a look at the following local variables of Py program, which has 3 functions, just as our previous function called the add function. Let's look at this. So we have these are the local variables: spam, boot, bobcat. As you see, this is inside this. So this will be spam is ant, spam is bobcat, spam is squirty, cavity, and my English is so bad. When the program calls, the frame object is created and placed on top of the call stack. This frame stores any arguments passed to in this case there are none, along with the local variable spam and the place where the execution should go when the function returns. So initially we have an initial frame object which contains all of these information. When A is called, it displays the content of its local variable, which is AND. When the code in A calls function B, a new frame object is created and placed onto the call stack above the frame object for A. The B function has its own local spam variable and calls C. A new frame object for C calls is created and placed onto the call stack, and it contains C local spam variable. As the function returns, the frame object pops off the call stack. The program execution knows where to return to because the return information is stored in the frame object. When the execution returns from all function calls, the call stack is empty. Makes sense. Figure this shows the state of the call stack as each function call is called and returns. Notice that all local variables have the same name spam. I did this so I the fact local variables are always separate variables with distinct values even if they have okay, so we have empty, then we have A, B, C, and then As you can see, programming languages can have separate local variables with the same name span because they're kept in separate frame objects. When a local variable is used in the source code, the variable with the name in the topmost frame object is used. Crazy. Weird. Every running program has a call stack, and multi-threaded programs have call stack for each thread. But when you look at the source code of a program, you can't see the call stack in the code. The call stack is stored in a variable as well as instructions automatically and in the background. It is like a programming language feature, right? The fact that call stack doesn't exist in source code is source code meaning the code you write, not the actual source code of the program. Is the main reason recursion is so confusing to beginners. Recursion relies on something that programmers can't even see. Revealing how stack data structures and call stack work removes much of the mystery behind recursion. Hooray! Functions and stacks are both simple concepts and we can use them together to understand how recursion works. Yippee! What are recursive functions and stack overflow? A recursive function is a function that calls itself. This shortest.py program is the shortest possible example of this. So the shortest possible, all shortest dot possible. So if you look at the actual execution, कॉल स्टैक अभी इनिशियली स्टार्ट हुआ देन हमारे कॉल स्टैक में वी विल हैव यहाँ ऊपर में शॉर्टेस्ट नाउ दिस शॉर्टेस्ट वी गो एंड ट्राई द शॉर्टेस्ट राइट ये कॉल्स शॉर्टेस्ट दिस विल गो wait this is a picture reference this is a picture reference yes I knew this was a picture reference this was a picture reference since the funny. Since the call stack uses the computer's finite memory, this program cannot continue forever. Obviously, because the frame object has to take physical space, right, in memory. It just can't linger in some void. The way an infinite loop does is the only thing this program crashes playment. The view is must maximum recursion depth exceeded. The kind of bug is called stack overflow. This is popular one. The constant function calls with no returns grow the call stack until all the computers. I mean, the thing with return is that it's responsible for popping it. So if you don't have it, if you don't have that pop condition, then you're asking for trouble, right? To prevent this, Python and JavaScript interpreters crash the program after some limit of function call that don't return value valid. The limit is called the maximum recursion depth or maximum call stack size. For Python, is set to around 1000 function calls. For JavaScript, maximum generally less than 1000 or so. The think of stack overflow as happening when the call stack to why that consume is yeah. Stack overflows don't damage the computer. The computer just detects that the limit of function call without return has been exceeded, has been reached, and terminates the program. At worst, you will lose any unserved work the program has. Stack overflows can be prevented by having something called the base case, which is explained next. I mean, the author was right. After understanding what the call stack is, it does kind of take away a bit of a mystery, if not all, from recursion. Right? So you pretty much have a frame object. So this is called a frame object, which contains line of code which call which called the func uh, arguments to the func, and then we have local variables, right? And we have a bunch of that. So and उसका ये हमारे पास bunch से bunch of frame objects से बना है. Cool. The Stack Overflow example has a shortest function call that calls shortest but never returns. To avoid a crash, there needs to be a case or sort of circumstance where the function stops calling itself and just returns. The return means popping from the stack. This is called base case. By contrast, a case where the function recursively calls itself is called recursive case. Make sense? Oh, crazy. All recursive functions require at least one base case and at least one recursive case. Obviously, if you don't have a recursive case, then you're not recursive. And if you don't have a base case, then you're inviting for stack overflow. If there is no base case, the function never stops making recursive recalls and eventually causes stack overflow. If there is no recursive case, the function never calls itself and is an ordinary function or a recursive one. When you start writing your own recursive functions, a good first step is to figure out what the base case and recursive case should be. Take a look at the shortest with base case, or by which defines shortest. Okay, so we say def shortest with base case, make recursive call, print shortest with base case called, make recursive call. If not, make recursive call, base case, printing done from base return, else recursive case, false. Uh, uh, I think what's happening, as I understand it, to learn. So if not, if this is false, but it will create that false anyways over there. So uh, starting with a base enough. So yeah, that returning from recursive case. Yeah. So it will run maximum two size रहेगा stack frame मतलब call stack का, because that is how it is made. It's important to note that when is recursively called then returns, the execution doesn't immediately move back to the original function call at 4. At 4, if you mean at 4. Why though? Code before and after the recursive code. The code in the recursive code can be split into two parts. The code before the recursive call and the code after the recursive call. If there are two recursive calls in a recursive process, oh yes, the important thing to know that reaching base case doesn't necessarily mean reaching the end of the recursive algorithm. It only means that the base case won't continue to make recursive calls. For example, consider the count down and up program whose recursive function counts from any number down to 0 and then back up to that number. So we have print number. If number equal to 0, reach the base case return. Else else we print, we count down and up number -1, print number returning. क्या होगा? When we give 3, this will return 3. अरे ये क्या हो गया? My bad. It will first return 3. Okay. क्या 0 हुआ? नहीं. Else recursive case 2. तो 2 पे आए, right? And then ये आया 1 पे, and then 0 पे आए. And the moment we come at 0, we pop it, and then this comes at 1, 2, 3, essentially. 3, 2, 1, reach base case, 1, I mean, yeah, reached. Obviously, this is reached. When we reach that. This will obviously say reach base case, which return, right? The moment that thing returns, it says printing 1 returning. Remember, every time a function is called, a new frame is created and pushed onto the call stack. This frame is where all the local variables and parameters such as number are stored. So there is a separate number variable for each frame on the call stack. This is another often confusing point about recursion. Even though from the source code it looks like there's only one number variable, because remember that because it is a local variable, there's actually a different number variable for each function call. Cool. When counting down up to 3 is called, a function is called, a frame is created, and that frame's local number variable is set to 3. The function prints that number variable to the screen as long as the number is in 0, counts down as recursively called with the function, and this it. Then the recursive. The pattern of making recursive function calls and returning the pattern of making consecutive recursive function calls and then returning from the recursive function call is what causes the countdown numbers to appear. Once this is called, the base case, the no more recursive call. However, this is in the end of our program. When the base case is reached, the local number variable is 0. But when the base case returns, the new frame process, the frame under has its own variable, which is always had. As the execution returns back to the previous frame, the code after the recursive call is executed. This is what causes the count numbers. Okay, so again, as you can see, so this fact that the code doesn't stop immediately when the base case is reached will be important to keep in mind for the factorial calculation in the next chapter. Remember, any code after the recursive case will still have to run. Any code after the recursive case will still have to run, of course. At this point, you might be thinking the recursive of the function is over-engineered and difficult to follow. Why not instead use an iterative solution to print numbers? An iterative approach uses a loop to repeat until it's done. It's usually thought as the opposite of recursion. Whenever you find yourself asking, wouldn't using a loop be easier? The answer is almost definitely yes, and you should avoid and you should avoid recursive solutions. Recursive can be tricky for both beginners and experienced programmers. And recursive code isn't automatically better or more elegant than iterative code. Readable, easy to understand code is more important than any supposed elegance that recursion provides. However, on some occasions, an algorithm cleanly maps to a recursive algorithm. Algorithms that involve tree-like data structures and requiring backtracking are especially suited for recursion. These ideas are further explored and to and fro. Recursion often confuses new programmers, but it's built on a simple idea that a function can call itself. Every time a function calls itself, a new frame object with information related to the call, such as local variables and return address for that execution, to move with the function is added to the call stack. The call stack, the call stack being a static object can be altered only by having it added to or removed from its top. This is called pushing and popping the stack as well. The call stack is handled by the program implicitly, so there is no call stack variable. Calling a function pushes a frame object on the call stack and turning on the function. Recursive functions are recursive case, and those in which recursive calls it wait in the base case. Those are the functions of returns. If there's no base case or bug prevents the base case from being run the execution. Recursion is a relational technique where there's good. You can find introduction to recursion as an recursion press the YouTube channel comes also. What on earth is recursion? Oh,
I think I've on fairly strong whatever. Look at it very briefly here.
crazy. You can install the show call stack module for Python. This module has a show call stack function that you can place anywhere in your code to see the state of the call stack at a particular point. You can download and oh, wow, this is interesting. I'll do that. in general, what is a recursive thing? A self-referential thing. So the code of the function, the arguments, the return type, and the next line of code, that recursive case that calls the function, say something like, so you push j, you push q, you pop, you push k, then you pop again j, you bacha. uh yeah, so this is next show. Let me just go through some of these videos, see what they're about.
But then I will do this. I think I'm on fairly strong ground when I say that we haven't yet in Computerphile done recursion. This can get extremely hard. It is difficult to get your head around recursion sometimes.
Crazy.
In one way, you can take a very mathematical view about it, just close your eyes. And if you're a pure mathematician who thinks, as we computer scientists would say, exclusively top-down about things, you can say, oh, it's just a formal definition. You know, here's an example of something you can do recursively. Factorial of n is equal to n times factorial of n minus 1. And if you're used to mathematical thinking, well, that's absolutely all right. Of course, they will then raise arguments and say, but you've got to stop that. You're just going round and round, chasing your own tail, because what about factorial n minus 1 then? Well, factorial n minus 1 is the same as n minus 1 times factorial n minus 2. And a mathematician will say, oh yes, all you're doing is relabeling the n's. You know, what was n now becomes n minus 1, and so on. And yes, that's quite right. But at the bottom of all of this, you've got to have a way of dropping out and terminating this
aka the base case.
succession of things defined in terms of themselves. Your way out of all this is that when you hit factorial 1, that is defined to be 1. So let's take an actual real example of this, and one which we will later develop with a program. What we're saying, I'll abbreviate it now as fact rather than factorial. Factorial for, from this definition, is 4 times whatever factorial of 4 minus 1, 3 is. But factorial 3 is 3 times whatever factorial 2 is. Factorial 2 is 2 times whatever factorial 1 is. But factorial 1 is 1. So there we are then. Factorial 4 is 4 times 3 times 2 times 1 is 24. Factorial, if you wanted to work them out on a computer, you can do it one of two ways. You can do it recursively, and this really, as we will see in its implementation, will need a stack.
Or you can do it iteratively, which is
Or you can do it iteratively. What does it mean to do it recursively? I will look at it very briefly here, but then I will do this for you on the stack. So here's our recursive.
well, this is the most elegant C code over here.
Factorial.
Written on parchment paper, by the way.
Put in a comment here saying this is the recursive version. What I'm saying here is, there again, those of you familiar with any of the C-like languages, you know, Java, C++, whatever, find this very familiar. The incoming parameter, or argument as it's sometimes called, is labeled n. The name of the function is factorial, and the answer delivered back by factorial will be an integer answer. So every time you call it, it expects an incoming parameter or argument, as it's sometimes called, and it will deliver you back an answer that's also another integer. Factorial is only defined for integers, not for real numbers, not for any other sort of thing, only for integers, and only for positive integers. It won't even work for negative ones. Okay, now this is almost like writing mathematics. It's almost like writing this definition I had up here, look. You say, if the incoming argument is 1, then my answer is 1. The factorial of 1 is 1. So I return to the outside world that wants to know, I return the answer 1. Factorial 1 is 1. Otherwise, I return back to the outside world that wants to know. I say the factorial of anything else is n times the factorial of the number n less than it. What the secret is here is that factorial of the next number below, you feed in as the so-called actual parameter the thing that is one less than the n you've got at the moment. So if you come with 4, I return back 4 times factorial 3. That's n minus 1. If n is 4, it's factorial 3. Oh gosh. What this means is I can't return the answer until I've
Worked
worked
out
out
what
what
factorial
factorial
3
3 is.
is.
So I dive back into this same piece of code, only this time it's still calling it n, but n has now
Change to.
changed into 3. So the first thing you have to get happy about is there isn't just one n. There's lots of them. They're all called n,
But they're
but
all
they're all different,
different.
and they all have to be managed and kept
AKA the
separately.
call stack and the frame object and the local variable that is being.
That's the first thing. There is not just one n. Recursion wouldn't work if there were. And that way of keeping them separate just naturally falls out. No prices for guessing. It's a stack. You need a stack to do this properly. Here's my main program. Here's its
Oh
environment.
wow, you got to start.
Here's its data. What I'm going to do from here, the main program, is to say, I want factorial 4. In order for it to work correctly and have its own local variables, which of course includes all of these different instances of n, in this case, you put on what's called another stack frame, another whole area of the stack, and you say, that one is going to deliver back the answer to factorial 4. But factorial 4 then says, can't work the answer out until I know what factorial 3 is. So remember, this smaller white one is going to work out factorial 3. It also does the usual trick. Oh, I don't know what factorial 3 is. It's 3 times factorial 2. So I've got to know what factorial 2 is. So here is the frame on the stack that will work out factorial 2. Finally, with a great sense of relief, factorial 2 says, all I know is that I'm 2 times factorial 1. There's factorial 1. At last. Factorial 1 says, I know what I am. I am the answer 1. The factorial 2 frame is waiting there
Yeah.
in what you might call a pending multiply. It's saying, I am 2 times whatever factorial 1 is. Factorial 1 says, here you go, into the pending multiply. The answer is 1. And then the same thing happens. Oh, so the answer of factorial 2 is 2. Where does that need to be delivered back to? It needs to be
Oh, it's
delivered back
beautiful.
into the frame below, which is positively gasping because it wants to do 3 times whatever factorial frame. But we just found it into the course with a web link to it. All I do with the value when I get it back is I just print it out and say the answer to factorial 4 is 24. That's back in the main program's area at the bottom of the stack. What you have to remember is that in these pending multipliers that we had, each one of them is holding on to a different
Value of
value
n.
of n as the left-hand operand in its pending multiplier. This is saying 4 times something, the one above it said 3 times something, 2 times something, and so on. And the answers cascaded back down and dropped out at the bottom correctly.
The sound a compiler makes when seeing a recursive code. Here's either, yeah, North Bay Python AI. Oh wow!
Okay, that's right. We're down to the last two. This is the home stretch, everybody.
Wait, this is the goat.
It's Alistair
That's
Whitehead,
him.
who is a local to the Bay Area and is the author of Automate the Boring Stuff with Python. He's here to tell us about recursion,
It's actually kind of weird.
defining it in terms of itself, which will probably become funny halfway through the talk. Please make him feel welcome.
I'm mostly known for writing this book, Automate the Boring Stuff with Python, and I've
Cool.
spent several years now teaching Python.
Oh wow, he created it. Crazy. Wow, this guy is the goat. Anyhow, show the simplified view of the call stack. This is a module similar to build traceback and network, but it's easier to use it. So Wow, so super stack on the end. Why do you use warp? Interesting. Know what's happening over here, but yeah.
particularly to beginners and trying to break down really complicated topics.
Yeah, so I guess we'll do the next topic in the next video. Yeah, it was a bit fun, yeah. No man, I had fun on it. So again, each chapter is I would say a beefy around 45 minutes to half an hour if you're going through it. So yeah, W, I think we'll get more used to this. Hopefully, I'm able to give more time into learning other stuff. But let's go through this video just a bit to see what's happening.
And put them simply. And I've been thinking about recursion because people think of recursion as this advanced, intimidating topic. And really, people think of recursion is hard or recursion is confusing or they don't really understand recursion. So recursion seems like magic. At least that's what the Google search results say. I like number 5. Recursion is bad. So I've spent a lot of time trying to figure out how can we explain recursion in a way that's very approachable. So I've put together this talk, which requires no background in computer science. You only have to understand the basics of Python programming to understand this. But before I get into this talk, there is something I have to do. It's just something we have to get through. So I'm just going to go into it, and that is go through all the recursion jokes. Just get it out of our system. To understand recursion, you must first understand recursion. Ha ha ha. Gets funnier every time I hear it. There's the dictionary definition of recursion, which ends with see also recursion. If you Google the word recursion, the Google search results will say, "Did you mean recursion?" with a link to the Google search results for recursion. I like my coffee like I like my coffee. Recursive. I'm so meta, even this acronym is meta. And finally, there's the mythical creature, the recursive centaur, which is half horse. It's a data structure. And the reason that happens is because 5 factorial is 5 times 4 times 3 times 2 times 1. So the first thing that you need to learn about recursion is that recursion is overrated. No. So recursion is still an important topic. You should learn about recursion. It's very useful and very necessary. But I see a lot of people using recursion when they don't really have to use recursion. And this is especially true for a few examples when we introduce recursion to students and beginners. There's a few examples that are always used. I'm going to cover 2 of them right now. The first is factorial, and I'm going to cover why this is recursive and why it's also a terrible thing to use with recursion. So factorial is a really simple math concept. 5 factorial is 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. You can kind of get the idea of how this works. So if you think about it, factorial has a recursive nature because 5 factorial is the same thing as 5 times 4 factorial. I mean, if you do the math, it checks out. So for positive integers, you can have any number factorial equals number times the factorial of number minus 1. You can see that the definition of factorial includes factorial. It has a recursive nature. There's an exclamation mark on either side of that equal sign. So that means we should be able to write some code that does this, right? We can have a factorial function. It has a number parameter, and it returns number times the factorial of number minus 1. And this seems pretty simple. It'll work, right? No, it actually doesn't work at all. We see that recursion error again, that stack overflow. And the reason that happens is because 5 factorial is 5 times 4 times 3 times 2 times 1. But what our code is doing is
It's going to all the
using
negative one, yeah.
to go to 0 and -1 and -2. And remember, every time we make a function call, we're pushing a frame object onto the call stack. And that's going to use up a little bit of memory. So we can't do this forever because eventually we'll just use up all of the computer's memory. And so what a stack overflow is when your recursive function doesn't stop recursing and it keeps recursing forever, and then eventually it'll eat up your memory. Python actually has a built-in limit of 1,000 function calls that you can make without returning. This limit is kind of arbitrary, but it's big enough for most purposes. You can change it, although I really wouldn't. It's best to just think of it as yeah, it's best if you just accept that 1000 is the limit. Okay, so we need to change this function. Here's a hint. 1 factorial is 1. So if we just check if our number parameter is 1, we can just return 1. This is called the base case. So it's the set of circumstances where your recursive function will stop recursing. And the other half of that is the recursive case, which is the code that does the recursion. Now, in every single function that you write that's recursive, you have to have
It's
these
pretty
statements.
much what we learned.
So our factorial function is exactly like our ABC function, except it's factorial, calling factorial over and over and over again. Just think about the call stack like that deck of cards. You can only see the topmost card. So this is what the call stack looks like when we do our recursive factorial function. So it starts in the upper left. We're setting number to 5, and in that function call, it has
So
to
we have
return
like
5
that's good.
times
That's good. I can cover this
multiple
video.
loops, which means we have to call the factorial function again. So we're putting a new frame object on top of the call stack. And in this frame object, number is set to 4. Notice that there are multiple local variables named number. The number that equals 5 is still there. It's just underneath the topmost
Yeah.
frame object. So that's another thing that people get confused on. There's going to be multiple number variables. And so in that function call, we call factorial of 3, which calls factorial of 2, which calls factorial of 1, and that's our base case. It just returns 1. It doesn't have to do any more recursing. So now we're returning, which means we popped the frame object off of the call stack. And that reveals that the frame object where number equals 2. And that one can return now. It just returns 2 times 1. And that pops off, and then we return 3 times 2, then we return 4 times 6, and then we return 5 times 24, which returns 120, 5 factorial. So I hope that diagram helps, but it's still kind of confusing. Factorial is actually a pretty bad example to introduce someone to recursion, because you have this line of code, and half of this line executes before all the recursive calls, the number -1 part, and then the other half executes after all of the recursive calls have returned the return number times part. It's sort of like I'm telling you a story about number -1, and then I get distracted with multiple levels of other stories, and then I finally come back and I finish telling the story of how return number times that return value. So factorial really isn't the best educational example for recursion. If you still find this a bit more difficult to comprehend, here I've sort of hard-coded several functions. So there's factorial 5, which calls factorial 4, which calls factorial 3, and so on and so on. And you can see here, like, oh, here's where the 5 times 4 times 3 times 2 times 1 happens. Our recursive factorial function is doing the same thing, except with just one function instead of separate functions. And if that's still confusing to you, you can just use the iterative version of this algorithm. Just a simple loop. It's fine. There's no reason, like, recursion isn't automatically more elegant than an iterative solution. This code works. It's pretty readable. It's great. There's actually, I mean, recursion is not more powerful than iteration. There is nothing that recursion can do that you can't do with just a loop and a stack, and I'll prove it. Okay, so I've shown you the recursive factorial algorithm, and I've shown you the iterative recursive algorithm. I have also created a monster, which is the iterative factorial algorithm that emulates the recursive factorial algorithm. Behold, look upon my works, ye mighty, and despair. This does calculate 5 factorial. I don't really have time to explain all the code, but suffice it to say, I've created my own call stack with a Python list. I have quote-unquote frame objects that are just Python dictionaries that hold the quote-unquote local variables, even though there are no local variables in here. It's all global variables because I have no functions. It's just a while loop. The body of the while loop has all the same code as the body of the recursive factorial algorithm. I split it up into 2 parts. There's the part that's the start up to the recursive call, and then the second part is after the recursive call to the end of the function. And whenever I quote-unquote call the recursive function, I'm just pushing these quote-unquote frame objects onto the quote-unquote stack. And then whenever I quote-unquote return, I am popping them off the quote-unquote, am I doing that right? Yeah, quote-unquote call stack. So this shows you can do this with any recursive algorithm, by the way. Everything you can do with recursion, you can do with a loop and a stack. There's nothing magical about recursion at all. But please don't do this ever. Okay, so, if recursion isn't more powerful than iteration, and recursion is often harder to understand than iteration, why should we ever use recursion? So I thought about this a lot, and I came up with an answer. And then I thought about it some more, and I came up with a better answer. Recursion maps very neatly to problems that have a tree-like structure and also require backtracking. You really need to have both of these features for a recursive algorithm to be very, very useful and elegant. Fortunately, there's a lot of stuff in computer science that involve trees and require backtracking. A tree is really just a node that branches off to two other nodes, and then these nodes branch off to other nodes, so it's naturally recursive. And if you think about it, a list is really just a tree that has one branch on each node, so list can also use recursion as well. A maze has recursive solutions because really a maze is just a giant tree that you can, from each node, take one of several paths from, which take you to another node, and then you can choose one of several paths from that. Every once in a while, you'll reach a dead end, so you'll have to backtrack to an earlier node. This is used in a lot of pathfinding and AI algorithms as well. Your file system on your hard drive is a tree. You have folders that contain other folders. That's recursion. So if you don't have a need for backtracking and a tree-like structure, you really don't have to use recursion. And sometimes it's a tool that you shouldn't use. Like, what if we try to calculate the factorial of 1001? Remember, Python has a limit of 1000 function calls. So if you try this, the recursive factorial function doesn't even work. It just causes a stack overflow. There is a way around this, though, and it's something called tail call optimization or tail call elimination. So this is used when you just have large problems that require a lot of function calls. If you redesign your code so that the last thing, what the tail of your recursive function does, is make the recursive call, then technically you don't need to hold on to the local variables because there's no code to run after that recursive call returns. So that means you can get rid of the frame object for the current function call off of the call stack, which means that the call stack never grows inside. I know I'm in size. I know I'm kind of rushing through this. But basically what this means is that tail call optimization allows you to prevent stack scenes. But the thing is, the CPython interpreter does not implement post by Guido van Rossum. Awesome. The reason, other than that it encourages you to bangle your code, but there's another reason for it. Well, the short answer is it's simply unPythonic. The longer answer is explained in a few blog posts by Guido van Rossum. So you can't even use tail call optimization in Python. It's totally irrelevant. And there's a second problem that we always use when we're explaining recursion to beginners, and it's also a terrible candidate for recursion, and that is the Fibonacci sequence. Oh yes, it's great. So if you don't know about this, it's a sequence of numbers. The first two digits are 1 and 1, and the next digit is just the sum of the two previous digits. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and so on forever. You can write a function that says, okay, find the nth Fibonacci number. And this is going to be a recursive function, or it can be a recursive function, because Fibonacci has a recursive nature. The nth Fibonacci number is just the sum of the nth minus 1 and nth minus 2 Fibonacci numbers. And the base case is that the first and second Fibonacci numbers are both 1. So we can write a function like this. And it works for really small numbers. If you try to calculate the 35th Fibonacci number, that'll surprisingly take several seconds. And if you try to calculate the 100th Fibonacci numbers, that will take several centuries. And the reason is because each call to Fibonacci generates 2 more calls to Fibonacci. So it's like a hydra. Every head you cut off, two more grow in its place. And this means we're doing a lot of work, an exponentially growing amount of work. And worse yet, a lot of that work is redundant. Like we're making multiple calls to Fibonacci 4 or Fibonacci 3 right here. So the trick around this
Please memorize
is
is
to
to
cache all the return values so that the first time you calculate Fibonacci of 4, you remember that. So in future calls with Fibonacci of 4, you can just return that cached value instead. And that prunes away this tree and removes all the redundant work. But again, that's sort of a trick you have to do just so you can solve a problem that iteration doesn't have to begin with. Now, this technique is called memoization, which your phone will always want to autocorrect to memorization, but it's memoization. We can just, create a cache
yeah,
and
this comes in
start
DP,
using
yeah.
also good outside of recursion, but it's a speak. So you can just use the functools.lru cache decorator, and it does the exact same thing. You can do this with any function. It's also good outside of recursion, but it's especially useful with recursion. LRU stands for least recently used. It's a very common caching algorithm.
Cache
But
replacement
again,
model.
that's just to fix something that iteration doesn't have a problem with anyway. So I hope I've gone and explained how recursion is not one base case and one recursive case in your recursive function. With recursion, you can do with a loop and a stack. There's nothing that it doesn't implement it in the interpreter. And that's it. That is everything I've covered. I'm really glad that I was able to get through all of this in 30 minutes. Here's where you can download the slides, and you can reach me on Twitter and at email. Thank you so much.
So guys, I will end this up. This was great. Our next video will be recursion versus iteration. And where's my video? So see you in the next video. Bye bye.